copies. If you don't, just send me an email real fast, and I will send you all a link. Real quick. So, before we get started, I want to emphasize this little item right here. This is the OSI model. What the OSI model basically is it is a conceptual way to understand what's going on in the back end of a computer. And it's a networking model, but it works really, really well for understanding kind of the architectural approach to building and designing web pages. It's a really good troubleshooting tool. And after we go through the presentation, we'll kind of go into it and talk about it. And as we present things like the networking layer and talk about networking later on in the program, we'll reference this model. And the same thing when we talk about security, we'll reference this model. So you guys have a quiz this very first week, and I need you all to take a great deal of time and try to memorize this. And what we really looking to memorize is this first column on the left. And the reason I need you guys to take the time to memorize this is because it is a reference point that we will use throughout. So when we talk about when I explain to you guys about how networks work and why they work the way they do, having this as a point of reference is going to be immeasurably useful. Understanding that what ports and protocols are and why they exist on certain layers of the OSI model and why it is that makes sense will make your lives much, much easier. And so that's the reason we have this quiz. So I need you guys to take some time, put some effort into studying this thing, because it will serve you throughout the rest of your career. A quick story. I've had 2 job interviews in which we referenced this piece of information. These are both security-related jobs. So, but they basically had me draw this out, and we talked in detail about it. So it's not simply, a pie-in-the-sky object. It's not something that, it's useless. It is something that can be used for troubleshooting. It can be used for things like job interview questions, because it really does draw down your conceptual understanding of what's going on in the back end. So again, I think it's totally worth your time, which is why I have 5% of the class basically dependent on it. Enough said about that. So when we talk about the internet, we talk about servers, we talk about networks, and we talk about design of all of this, we have to really take a look at what history entails and why the internet is the way the internet is. So a long time ago, 50s and 60s, basically what we had this notion of connecting devices together through direct connection. So if I had a computer in San Antonio and I had a computer in Dallas, I could simply take a piece of cable, and it was telephone cable, but we could just take a piece of literally copper wire, and we could solder it in at one location, we'd solder it in at the other. We'd build some connection protocols, which I'll explain what those are in a few minutes, and then we would just communicate, right? And it would go through some centralized switching location, like the old Ma Bell telephone networks. So we had direct connections from one location to another. Now, this is incredibly simple, right? It makes a lot of sense. You have one computer talking to another computer, everything's fine. They're easy to construct, they're simple to administrate, and they rely on a centralized location to do their switching. So in other words, if I wanted to talk from my computer in San Antonio to the one in Dallas, I would basically send the signal to the switching office. They would switch my connection to that location, and then I would connect there. If I wanted to make another connection to, let's say, Houston or New York or DC or somewhere, I would basically send to the switching locations, and the switching would handle that connection. It would be a direct one single line connection. And as soon as the connection was done and I was tired of communicating, or I was finished my process, I would just say, okay, now shut it down. And this is a viable approach, but there's a problem. And a lot of the reason that this is a problem is because a lot of the money that was put into the development of the internet and its this kind of internetworking system that exists out in the world was really government driven, and specifically the Department of Defense. And so the idea to them of having a centralized single location to have all of their information pass through was terrifying. Because remember, we're talking 40s, 50s, 60s. This is the dawn of the Cold War. This is the period in which we're starting to see the idea of people potentially nuking things in our country. And because of this kind of this fear and this desire to make sure things are redundant and robust, The military said, look, we can't have everything go through these centralized switching offices alone. Because if they do, what could happen is those things could get bombed, they could get disrupted, lines could get cut, and this entire form of communication that's being built would shut down. And so that was kind of a very, very clear indicator. So, and a clear drive. So what people ended up doing is they said, how can we solve this problem by decentralizing all of this communication and instead having everything move through all of the networks in a dynamic manner. And so the way they do this is they create what's called a logical layer or an abstraction. And they take this notion of, remember this, we're going to solder one location to another location, and instead of handling that connection at that physical layer, what we're going to do is we're going to create some addressing information, and we're going to stick it on the front of the messages we want to send and on the back of the messages we want to send. And then this addressing information will allow us to take that information and route it to whatever locations we want. And we could send it through any number of channels, any number of locations, and it doesn't really make any difference how it gets there. So what happens is then we create this web network, this mesh of communications. So when we send signals, emails, let's say, a portion of the email could go through Vancouver, a portion could go through Washington, a portion could go through Houston, a portion could go through San Francisco, a portion can go through Taipei. And as long as it found a route that eventually led it to the end location and had the routing information needed to get there, it would get there. And sometimes it'll be faster, sometimes it'll be slower, and sometimes you'll lose some packets along the way. But at the end of the day, as long as you get the entirety of the message there, there's no single way to shut down the entire network. And this is kind of the point of this notion of logical versus physical connections, all right? And again, think about this in terms of physical locations, about like addresses. So addresses, like your physical addresses. So if a physical address could be, you could live at 1234 Main Street, and at that location, that is the specific physical address. That doesn't mean that your house is there. Or it could be a trailer, it could be a house, it could be anything. Additionally, you could take that domicile and you could, in theory, move it, right? It's not necessarily tied to that, and it's not very common, but you understand that people who do like house moving or who manufacture homes who have specific addresses for a period of time. But the point is that that is a physical location, and it's not exactly the same thing. It's a logical location. So when we talk about logical locations, we talk about we're talking about two things. We're talking about IP addresses, which I think everyone might have heard of, and it's very common for people to see. You'll see there on the slide. There's IP version 4, IPv4, and to the right of that, you're going to see it's 168.192.0.1, and that is a very common IP address standard that most people are very, very familiar with. Below that is IPv version 6, and it is simply a longer, more engrossed version. The reason that IPv version 6 exists is because IPv4, we ran out. It's as simple as that. We're out. IPv version 4, basically the way it works is there's the lowest number you can have in each of those sections, those little separated by periods. They're called octets. Each one of those octets is 8 bits of information, and they can hold up to 256 pieces of data, from the lowest number being 0, the highest number being 256. And if you want to calculate the total possible options that you can have for that combination, would be 256 times 256 times 256 times 256, right? 1 for each position. And so that way you can run through the permutation of all the possible options. Well, if you do that math, it resolves to a relatively small number by comparison to the number of devices we have on the planet. Think about all the phones, think about all the televisions now, nowadays toasters, all of the computers, servers, virtual devices, all of these things need these these logical addresses. So what we did is we invented this second version. It's IPv version 6. And each of those little sections separated by a colon is called a word. And those things are just designed to give you more options out there in order to pick what it is logically that these devices are. The second way we notify or we handle things is physical addressing. So again, when we talk about physical addressing, we can talk about the notion of the actual wires connecting. We can talk about, well, that's physical connections, right? Whereas physical addressing, we're talking about the devices themselves. So we're talking about the NIC card or network, what is it, NIC? NIC, network interface card that you actually plug your devices into, or the wireless card you plug your devices into. They have a physical address associated with them. It's something that's put in by the manufacturers. They follow manufacturer standards, and it defines uniquely each of those devices. And these are both methods and mechanisms we can use to identify logically what this device is. So when we now we've taken this notion of logical addressing, and we've kind of talked about this notion of being able to send signals from one location to another with this little bit of addressing information, and that's called packet switching. And when we talk about packet switching, it's important to note that you want to take the messages you want to send, whether they be email or whether they are streamed video or downloads, it doesn't matter. And you want to send them into small chunks. And the reason you want to do this is because that way you can get the pieces out quickly and verify that each piece is correct and request replacement pieces for the pieces you need replaced, and otherwise you need to sort and order and deal with each of the pieces that you have. And this is kind of the whole nut of packet switching. All right, any questions? Does all this seem to make sense to everybody? So far, excellent. So we have packet switching. Now what? What do we do? So again, let's talk about this notion of email. What are the things you need to compose, transfer, and move an email from you to somebody else? Everybody uses email on a regular basis, right? Just think in your minds, what's the first thing you need? You're going to send an email to your friend. So you open your computer, and then you open whatever the client is that you're using to send that email, right? So that could be a web-based client. It can be a like Outlook, or it can be Eudora, or whatever the specific application is. And then you take that and you compose your email. And inside of that, you're going to put some specific pieces of information. You need to put in things like the target email address. You need to put in like the subject and then the content of the email. And so there's a set of very specific governances and rules. And then when that email is sent out, it needs to be sent out to something, right? There's a magical thing that happens where your computer says, I'm going to send it to so-and-so at gmail.com. Well, that process, the way that works is it splits up those emails into the pieces. It labels them with what they are. It assigns, takes that to location. It goes out and does something that's basically a DNS lookup, but I'll explain what that is in a few minutes. But it does a lookup for what the @gmail.com means, and then it sends it out to that server. That server gets the packets in, reassembles it, and then sends it to the inbox of the recipient, right? So now, and then they, in turn, do what? They open it up through the clients that they have and do the same thing. Now, if we go back for a moment to this OSI model, and this is kind of where we start to see the value. If we start at the top, when we talk about email, we can start by saying, look, we have applications, and then things start to happen. The application layer is where the human interacts with this stuff, with this nebulous idea. They compose the email, and then things start to happen down from there. So the presentation layer, things will become encrypted. Session layer, it ensures that there's connections between devices. And for the web designers in the program, you're going to know about session variables, and we'll talk about those later. And when you get in the later classes, it'll make a lot more sense. We talk about the transport layer. It deals with TCP, which is your transmission control protocol. So it deals with how things handshake and how the data is transmitted from one location to another. The packets themselves are kind of assembled at the network layer, and that's where IP addressing occurs. And then down from there, we go down to the data link, and then which is MAC addressing, and then which is physical addressing, and then we go down to the bottom, which is the kind of physical connections, the wires themselves. So again, from the email's perspective, you go through, create the email at the top, and then it kind of walks its way all the way down each of these layers. So it gets to the bottom, it gets sent out. Thanks, Full Sail Tool. That was great. So it gets sent out, and then again, it walks itself right back up this stack to get back to the application layer for the individual to use it. So does everyone follow that? Make sense? Good, 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 good. All right. So real quick, protocols. I mentioned this term before. Protocols are all about following a set of very clearly defined rules that govern how things are supposed to happen and what the computer is supposed to do at given periods. So the reason you need protocols is because, remember, when you program a computer, what does it require? It requires you to be diligent in telling it to do everything. So you can't leave anything to chance, right? I'll talk about something called a race condition. You have two processes that run at the same exact time. What are the possible outcomes? You could have let's say process A and process B both start at the same time. The possible outcomes could be process A could finish first, process B could finish first, or they could finish at the same time. Well, I guess, or one of them could not finish. So you have a series of possible options, and in each of these cases, you have to create rules to govern how things occur. Protocols basically handle that for you. They follow a set of governances and a set of rules to do this. So again, when we talk about things like email, we use Simple Mail Transfer Protocol, or SMTP, to do that. You guys are going to be very familiar with the bottom. Web pages, what do they use? Web pages are served up through HTTP and HTTPS. These are the protocols or rules that govern how it is the web pages work. File transfer protocol. So we can talk, or secure file transfer protocol is the same thing, SFTP, FTPS, or FTP. These are all exactly the same thing. And remember now, think of protocols, you're going to always want to think of them as a set of rules. So again, protocols can also be used on the other end, right? So if you have a specific set of protocols that dictate what applications get used, that's what's going to happen, right? So the protocols for handling things like docx would be you would use whatever Word application you have. So it's whether Word or I don't know if Pages does it or what are some of the other, like there's a bunch of free ones out there, Star Office, Open Office. These would basically act in the same way. Are you guys familiar with this? Does all make that all make sense? I think there's a yes. Excellent. All right, so mentioned before this notion of domain name servers when I was talking about mail. Remember, we were going to send out an email. It's going to go to @gmail.com. How does it get to @gmail.com? What is it that allows the computer to know that gmail.com is a specific place? And where is that place? Well, the way it works is, remember that we talked about before this notion that we have IP addresses. Logical addressing is tied to machines. Well, when logical addressing is tied to machines, that means that those machines themselves have that logical address. So somewhere out there in the world is a device that is associated with an IP address that is associated with things like gmail.com. And the devices, the servers that are out in the world actually hold this information are called domain name servers, or DNS. DNS are out there specifically to do nothing but translate the information that you have in a domain into a functional IP address, so that way the computer knows where it is. Because to a computer, it doesn't really want to know anything beyond the actual location. And computers are terrible at understanding language by comparison to how well they understand very clear addressing. So we have these devices called domain name servers, DNSs, that are out there that just do this for them. All right, you guys got this, because this is kind of important, especially for the web kids, people, adults. Sorry, you know what I meant. All right. So again, DNS. It takes the uniform resource locator address or URL, converts it into an IP address from a repo that it has. Okay. Just so you know, there's 13 main servers in the world. All right, and well, I guess 13 groups of servers. You'll see them in a second. They're all over the place. They're all over the place, and they're all basically they're popping up all over the place even more and more often. And so what happens is, anybody here ever gone out into the world and set up a website and registered a domain name? Have you guys ever done that? Right. So how long does it take to propagate? I have a couple yeses, I have a couple no's, I got all the time. So how long does it take to propagate a domain name out in the world? To register it? How long until it's active? You've got a few hours up to 24. I've had it take 36. I've heard it's taken as long as 72. The reason for this is because it needs to propagate to all the other servers throughout the world. So they say it can take up to 72. I've never seen that happen, but I'm also very American Eurocentric, so I have a very limited bandwidth in my targeted markets for the type of work I do. So that being the case, very, very short amount of time. Whereas again, if you're doing some of the emerging markets, some of the other markets out in the world, I guess I could say Asia and so forth, and you're developing here and registering here, you may have longer wait times. All right. So if we break this down, this is from a couple of years ago. 34% of basically is Europe. We have North America about 28% of the DNSs, and then we kind of break down from there. So Asia is about 17%, South America is about 8%, and then we get down to like Oceania, which I think is at 8%, Africa is 5%, and then the Middle East is 3% of the servers. So again, it's important that you kind of know that there's a distribution around the world. So again, when you think about things like targeted markets, it's important to kind of keep that in your head. So in brief, since we're talking about URLs, let's kind of break them apart a little bit. So when we talk about them, just take a look at what we have here at the bottom. We have an example, and that is https://docs.google.com/presentation/d. Okay. And then / a big long thing, which goes all the way down to the second line, and then you're going to see a /edit. $, hashtag, I guess what you kids are calling it nowadays, slide equals ID dot something, okay? So what this is each of these pieces has a name. So we have the schema at the beginning, which is the protocol that we're using, right? Hypertext Transfer Protocol Secure HTTP, right? HTTPS. Then we have : / the domain. So what's the domain here? The domain is docs.google.com, right? If we really want to be technical, and that really is. And then we could say that there's a subdomain that's really kind of a subdomain within the google.com domain itself, right? And then we have, beyond that, we could have a port that sits in there, which is, we'll talk about what ports are in a minute. And then we have a path. Now this path, this is, again, for the web people, this is kind of important to understand. The path itself is the same exact conceptual path that you would use to find files inside of your local device. So when we say things like /presentation /d, those are folders. Those are files. So those are folders, and then inside of each one of those is eventually a file. So if we follow this thing down, we're going to get all the way down to the point where we can see that this portion right here, sorry about that. We get all the way down to the portion where we see that this is the 1 ML, blah, 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 huge identifier. That piece is going to be pointing at something else, which then has an edit function within it. So then after, all the way down to edit, And then what we have after that is we have a fragment. And so this fragment is signifying the specific slide. So what this URL is it's actually a link to this specific page in edit mode in this presentation. So it is what this presentation looks like in edit mode. Again, but now that you kind of get it, you should be able to take apart URLs at leisure, right? Because you now should be able to conceptually understand what's going on in the back end. Now, the last thing we have to talk about here is that :port, and that'll become important when we set up our virtual boxes, okay, because you're going to need to understand what ports are and what port forwarding is, and I'll get to that in just one moment. So now we've kind of given you kind of this overview of the whole thing. I think it's important to talk for a minute about servers, clients, and what those mean. So a server is simply a device that services something else. It is a server. It is a thing that serves. That's it. So you can do, a server can be a phone, it can be a Raspberry Pi, it can be a building-sized supercomputer. As long as it has a secondary device that is connecting to it, that is pulling data or using it for some processing purpose, it is a server. So that's important. We'll talk about clients in a second, but let's talk about server, and specifically let's talk about their operating system. So we talk about servers. On top of that, we're going to sit, this is hardware, right? So we have a physical device, or we have a virtualized physical device. On top of that, you're going to have operating systems that reside. And your operating systems do what? They control the hardware and act as a buffer between the hardware and the applications that run within the hardware, right? Because if you, again, think about it in this term, how many actual jobs do you do with the operating system itself? I'm yet to think of one. Even the administrative tasking within my MacBook or within my PowerBook at home or even on my Windows boxes, there's not a single task I do using the operating system. All the tasking I do, I use applications that sit within an operating system. So again, the operating system's job is primarily to simply act as a buffer and a controller for all of the hardware that exists within my environment. Now, this can also be said for mobile devices, right? So we talk about the most common. Windows is typically the most common in the PC market and kind of the personal computer market. And then we talk about OS X, and we talk about Linux, and there's a million flavors of Linux out there. And then we can talk about mobile. So mobile, there's iOS, Android, Windows Mobile, and maybe even others that I'm not aware of. But those devices and those operating systems, they're really out there for one purpose. They're really out there just to control and to contend with the hardware, so that way applications can be designed and developed to be placed within it. Again, think about it in terms of like maybe a bathtub and a boat. So we talk about hosts. Hosts are basically things that allow full two-way access to another computer. All right. It's not a term you're going to really need to know. It's just another computer term that's out there. Here we go, real quick. Web servers. This is an interesting piece. Web servers host web information. That's it. We'll talk about what the web servers are. Now, Linux is not a web server. OS X is not a web server. Linux, Windows, none of that are web servers. Those are simply operating systems the web servers reside in. They typically, oh, by the way, and so web servers typically use HTTP and HTTPS protocol. FTP servers, that's what they do. They serve FTP, file transfer protocol. They're file servers. Tor, this is for those people who want to play with terribly scary things. The Tor network's out there, and there are Tor servers. And I'm going to warn you right now, if you start playing with Tor, it can be dangerous. It can open you up to a lot of headaches. It also has a lot of power. So I like to include this for our kind of gray hat students, white hat students who want to go out and kind of look around into that seedy underbelly of the internet. I think it's worth the mention. Again, I'm not condoning it. And as long as you're doing things ethically, it's a great tool. Just have it out there. Again, we talk about the other end of the world, which is clients. So clients are the things that receive. We typically think about the web architecture. You have a server like Amazon.com or Google.com or what have you. These are locations that are out in the world. They're domains that exist. They have IP addresses, and they're sitting out there waiting for people to try to connect to them. The people take their local machine and do that process, right? They connect out to those devices. In that process, the people connecting, are the clients. That's what they do. And for web programmers, it's important to understand that what happens on the client's computer and what happens on the server don't always match. And what you can do on the server can directly influence what happens on the client, and what the client does can dramatically impact your code. And I say that from a security perspective, so I want you all to think about that. And for again, I don't remember the program, I'm sorry, it's Jay's program, and I wish I did remember it, but you server administrative types. From this perspective, you guys have to keep this in mind as well. It is incredibly important to understand how the client and the server work and how those connections can be overcome. And I mean that in a hacking sense. So browsers. So what are browsers? They're simply nothing more than an application that we use to reach out and to touch these servers that host web information, that host HTTP and HTTPS information. This is the tool that we use to get to that information. Browsers nowadays can host everything from Java, JavaScript, XML. They can host a host of different, Flash, all kinds of different stuff. And so that's what these devices or these applications are designed to do. But remember, they are applications. They sit at the layer 7 of the OSI model. That's what they do. They're at that layer. Same thing with FTP clients, right? An FTP client is an application that uses a specific protocol to connect to a specific type of server to interact in a specific way to transfer files. That's it. Here's a question for you guys. Can you have a HTTP and an FTP server on the same device? Answers would be cool. Yes, you can. How does the computer know what to do with it? If it gets a request, how does it know where things are supposed to go? The way we typically do this is through things called ports. Ports are just addresses that are inside of the computer. They are numerical values that tell the computer this piece of information that's coming in, this request, handle it in this way. That's all they do. So the same way that you could say, hold on one second, please. Sorry, we're getting sick, being sick. So the same way that you could say that you want to have items shipped into a certain country, and they may come in through boat on a specific port. They work exactly the same way. Common ports include, by the way, these are numeric. And so you have like HTTP. HTTP typically goes through port 80. HTTPS is typically port 443. FTP is 20 and 21. Simple Mail Transfer Protocol, SMTP, is simply done through 25. And DNS uses 53. These are not something that you have to memorize entirely unless you're server administrators, in which case you really need to memorize these entirely. But as far as the web programmers, the ones you guys really need to know is all of the ports that are associated with the protocols you use on a regular basis. So you really need to know 80, you really need to know 443. And you need to have those memorized, and if anybody asks you at any point, you should be able to rattle those off. So when we talk about web servers, we talk about physical devices, we're talking about applications that actually do the web serving itself within these physical devices on these operating systems. What are we talking about? Well, there are two major ones that are out in the world. IIS is Windows. It is the Windows web server. But the more common one, the open source one, the one that is predominant in the industry, is Apache. It is the gold standard of web servers. So Apache is simply a server, or it is a service, an application that runs on a device that serves pages. It sits and listens for connections on the ports you tell it to listen to, which is typically 80 and 443. And it hosts the information that's requested. That's what it does. You can tie languages to it, like PHP, like Python, but at the end of the day, it is itself nothing more than a tool for conveying the actual web requests that are out there. And then we also have another one called JRun, which has kind of become defunct, but I wanted to add a third option instead of simply saying that these are the only ones out there. There are more of them that are coming out all the time. People want to write their own. The world is changing with regard to this. It's not really a binary system. And you could go out and try as many as you want. But as far as the program is concerned, typically we're going to be sticking with Apache because it is, if you understand Apache, everything else will make sense as well, because again, it's a starting point and a really good building block. All right. These are not web servers. PHP, Cold Fusion, Python, Ruby, ASP, HTML, none of that is a web server. Those are all languages that are out in the world that can help you to do things, but they're not a web server, and you guys need to differentiate that. So you can have PHP on your web server, but that's not a web server. All right? Everyone get that? I'll take that as a yes. Excellent. So databases. Now, we talk about web servers from a building web applications perspective. We got to talk about databases because let's face it, if you're going to put stuff on the web, you're probably going to want to store information too. And you're probably going to want to build information in such a way that it's dynamic and it can be pulled out based on people's specific criteria. And you need to store that information somewhere, right? Well, the way we do that typically is databases. And these are just applications that house and organize data. Typically, databases do two things. They read and write data. And some people will argue with me. They say, Joe, but they also delete data. Well, yeah, it's true, but that's really just writing zeros back over the thing that was there, right? That's all they do. Now, web students, you're going to get into a little bit more of this when we get into the web program. You're getting into databases, DBS, and you're going to get to ADB. You're going to get inundated with this, believe me, both NoSQL and SQL versions. And then, in addition, I don't know if you guys deal with this in the other programs, but I suspect you probably will. And if you don't, it's relatively easy to pick up. Database administration is fun. We talk about database languages. Database languages typically are not exactly the same as normal programming languages. Normal programming languages tend to be object-oriented. They tend to be or linear, so that data kind of flows from top to bottom. When we talk about queried languages, we're talking about Venn diagram set-based organization of data. So look at what a Venn, V-E-N-N diagram is and understand that that's kind of how you program in databases. And I know it's going to be difficult for people to get their heads around, but if you get that notion in your head now, it'll make things easier later. And as far as those are concerned, we're talking about SQL for structured query languages, and then there are other languages out there like LDAP, which is a directory services language, which is basically kind of an internal authentication system. Most common databases are MySQL, MS SQL, Postgres. I'm very, very, very big fan of all of these. The top one and the bottom are free. The middle one is incredibly expensive, but has a lot of power. I'm not a huge Microsoft fan, but I can tell you that Microsoft SQL Server, they've done a fairly good job of. And I'm a pretty big fan of things like reporting services and a few of the other tools they have with it. All that to say what? In the program, again, web people, you guys are going to deal with MySQL. It's most common. It's robust. It's perfect for small applications. It's incredibly powerful, and it's a great step-off point. So when we talk about this, again, now let's talk about this. We talk about servers. We need to talk a little bit about users. We need to talk about trust. So we talk about users. Most people think of people, right? So you think of users coming into a website and signing up. But that's not the only instance and implication of this term. Users are simply accounts. And those accounts can be anything from a person to an organization, an entity, an automation, a process, a daemon. It doesn't matter what it is that's tied to. It's simply something that's out there that needs to have permissions assigned to it at an operating system or at an application level. So when we think about users, we need to think about it in terms of that. So later on, when you guys build your final projects, you want to think about things like service accounts. You want to think about how you organize data, how you organize users. So that way, we think about administrators, data, service data accounts. You need to think about the actual end users, what kind of users, power users, and so forth. Again, you need to get this notion in your head. That leads to this notion. Again, we've now delineated different kinds of users, right? So with each kind of users, you need to have, it kind of speaks to something called trust. Trust is not isolated to this user's concept, but it is something that kind of it's implied by. So what trust implies and what trust is about understanding a thing as what it's supposed to be and then assigning it a certain amount of permissions based on what it is. So trust determines the permissions that you're associated. Now, the interesting thing about trust is there's something called transition of trust. What this means is that, let's say I have two friends, John and Bill. And I don't really like Bill very much. I hope it's not Bill in the class, but you get the idea. So I have John and Bill. And Bill and I don't really get along. And Bill doesn't do me any favors, and I don't do Bill any favors. But John and I are really tight, and John and Bill are really tight. And so Bill needs my help moving, but he can't ask me. But what he might do is he might say, hey, John, why don't you come over and help me move and, bring any friends that you want. Who do you think John's going to call? Me. And do I want to go and help Bill? Probably not. I don't really get along with him. But because John asked me, I'm going to do it. The same thing can happen with services, with applications, with programs, with accounts. I don't necessarily have to have permission to do a certain thing. I simply have to have permissions to access a trusted object that can do a thing. And that trust can be extended incredibly long distances by this notion of transitive trust. Everybody get this? Excellent. All right, now, architecture. For the purposes of this program, we need to deal with two kinds of architecture. Client-server and peer-to-peer. Client-server is what we talked about just like 5 seconds ago, right? We have servers, like web servers, like Apache servers, serve information, and on the other end we have clients who connect to get that information. Client-server, exactly like that, just an architecture. Underneath that, we also have something called peer-to-peer. And I hinted at that with something called the Tor networks. These are, BitTorrent is where the Tor network kind of comes from, and it is this notion of doing file sharing by distributed service architecture. So basically what we're doing is that we're not having a centralized repository, but instead we're taking the information that we have, breaking it into pieces, and pulling small pieces from a myriad of connections that may be out in the world that are just sitting around waiting and just happily serving this information. So it's peer-to-peer. There's no centralized repository for the information. I simply find it through some mechanism. You happen to be hosting it, and then I pull it down from you. Anybody here who wants to get into any of the white hat hacking, you can get into, look at Kali Linux, K-A-L-I, And Kali Linux is, you're going to have to download it through the Tor network. Again, be careful. Make sure you have you check your MD5s, which you'll see you're hashing. But it's out there. You're going to use peer-to-peer networks to do that. All right. Do you guys have any questions for me about this topic? Again, this is a very high-level overview. This is just a quick talk to kind of get you guys prepped and ready for the content of the course. Anyone? All right, no questions. All right, well, thank you guys very, very much. I'm going to shut off the recording now, and I'll give you guys one last chance for any questions that you want to take offline, and then we'll call it a day.